known as DJB, the inventor of many crypto systems currently used on the internet, including 25519, Cha-Cha20 and Poly 1305. 我很荣幸跟大家介绍这个 Daniel J. Bernstein， 又名 DJB。那他是现在网络上很多密码系统的设计人，比如说25519，比如说Poly 1305跟 Cha-Cha20。好，那我们现在把场子交给Dan。
谢谢。This is a talk about cryptographic software. In case people don't recognize this picture, this is a picture from a movie called The Blues Brothers. Now, this is a documentary about American culture. The Blues Brothers tells you everything you need to know about the United States of America. And one of the things that the movie tells you is that the police in the United States are not very good at their jobs. Now, this is an old movie. It's from 1980. But it's still true today that the police are not very good at their jobs. Now, somebody else that's not very good at our jobs is cryptographers doing cryptographic software. For example, here is some cryptographic software from Microsoft. And this is in Windows 10. This was a recent announcement, well, not this year, it was before the pandemic. Actually, it was late 2019. And this said that inside SymCrypt, this is Windows cryptography. SymCrypt is the Windows cryptographic library. Inside SymCrypt, there was a bug which allowed anybody to take down any Windows server on the internet. This was a report in Forbes magazine. It said, it's a bug within SymCrypt, the core cryptographic library, responsible for implementing symmetric and asymmetric cryptographic algorithms inside Windows. Now, if you look at the details of this bug, then what happens inside the bug is a very simple mathematical computation. It's something that we teach students in number theory classes. It's the Euclidean algorithm. It's actually a slight different algorithm called the extended Euclidean algorithm. But the Euclidean algorithm is computing the greatest common divisor of two integers. You divide one integer by the other and replace it with the remainder, and then divide this integer by the next integer, et cetera, until you get to 0. It's a very simple algorithm, and it's something that textbooks tell you, here's the algorithm, here's the proof, it always works, just use it. Now, Microsoft implemented this algorithm, and they managed to make an infinite loop. The algorithm on some inputs would just run forever and forever and forever. How did they do this? Why did they do this? Well, when people write cryptographic software, they want it to go quickly. They want it to be as fast as possible. They also want it to be constant time. I'll talk more about that later. And so they don't use exactly the textbook algorithm. There are many, many different algorithms that people use, and so they make mistakes sometimes. There's many different algorithms, and sometimes people get them wrong. Another example from the NIST Post-Quantum Cryptography Standardization Project. This is about a submission called Falcon. It's one of a very small number of signature systems which are under consideration for standardization. And this bug said that the signatures from the Falcon software leaked your secret key. So then anybody could sign messages. Complete security disaster in the Falcon software. And then the comment from the Falcon software author, he said, the fact that these bugs existed in the first place shows that the traditional development methodology, being super careful, has failed. Okay, they fixed the software, maybe. They fixed this bug. But does the software work correctly now? Who knows? Maybe there's more bugs. One more example, Minerva. This one is a timing attack against elliptic curve cryptography. And this one, you can see many libraries mentioned here. libgcrypt, that's the GNU cryptographic library, Wolf SSL, Crypto++. These have issued patches to fix this timing attack. This is not a wrong computation. The previous bugs were incorrect computations. This one is a timing attack. The software takes different amounts of time for different inputs, and that leaks secret information because of the timing. Now they discovered this timing attack worked against many, many cryptographic libraries. Some of them fixed the problem, but are there more problems? We don't know. There was a paper a few months ago which was called "You Really Shouldn't Roll Your Own Crypto," an empirical study of vulnerabilities in cryptographic libraries. Now, this paper looked at 10 years of CVEs. From 2010 to 2020, they looked at all of the announced security holes in all of the major cryptographic libraries. And they found, well, 73 actual cryptographic vulnerabilities. Now, what does actual mean? They actually found many more CVEs. These libraries have announced many, many bugs. But some of the bugs are buffer overflows, or certificate mismanagement, or some other kind of non-cryptographic bug. It's a cryptographic library which does mathematical computations, cryptographic computations, and it does things like TLS management, certificate management. And sometimes many of the vulnerabilities are problems outside the cryptography in a cryptographic library. 73 bugs over 10 years. Those were in the actual cryptographic computations. And out of those, 11 were severe. Now, what does severe mean? Severe means that the authors of the cryptographic library say, ooh, you can definitely use that to expose user data. What about the other 62 bugs? Well, those were not called severe. That means maybe they expose user data. We don't know. And then these bugs have been fixed. What about the next 73 bugs? Who knows? There are many reasons that cryptographic software is becoming more and more complicated and adding more and more bugs. Of course, we try to fix the bugs, but there's these pressures on the cryptographic ecosystem. And let me go through the main pressures here. First of all, on the left side here, people want the cryptography to be fast because cryptography is applied to all of your data. Everything that you're sending through the internet, everything that you're storing encrypted on your flash or on your hard drive, that is using cryptography. And it has to be fast enough to handle all of that. Now, in my title for today, I mentioned post-quantum cryptography. And this is trying to protect the cryptography against quantum computers. Right now, IBM announced a quantum computer with 127 qubits, the Eagle, but that's not big enough to be a threat against cryptography. They say their next processor will be 400, and then 1,000. And Google has been working on their own processors, and Microsoft is trying, well, not very well, but maybe they will succeed and build their own quantum computer. Once somebody builds a big enough quantum computer, then lots and lots of cryptography is broken, and we need to replace it with cryptography that survives quantum computers. Maybe code-based, hash-based, isogeny-based, lattice-based cryptography, or multivariate quadratics. Where's Boyan? Here's Boyan. Our top expert on multivariate quadratics in the whole world is sitting right there in the corner of the room. All right. Another pressure on cryptographic software is these timing attacks. When cryptographic software takes different amounts of time, it can tell you secret information. I'll give you an example later with actual software of where these leaks come from. Now, people look at these pressures. We want cryptography to be fast and post-quantum and secure against timing attacks. And people say, okay, we can write our cryptographic software to be as fast as possible. And then we can write our cryptographic software to only use post-quantum algorithms. And we can write it to be constant time. But that's complicated. It's easier if you build specifications, if you design cryptographic systems where you're thinking, how can I make the software easier to build? But it's still very, very complicated in the end. If you look at the post-quantum specifications, which are trying to be post-quantum, trying to be fast, and trying to be constant time, there are many, many pages just defining the algorithms. And then when you write software for these post-quantum systems, it's very, very complicated. There are many, many implementations of many different functions with many mistakes that people make. Here's an example of how complicated things get. Now, this is one of the simplest cryptographic functions, SHA-3, the Keccak function. This function, if you look at the specification, it's possible to define it in less than one page. And many cryptographic functions are much more complicated. This is a reasonably simple, one of the simplest cryptographic functions. If you look in the official code package from the Keccak team, then they have some reference C code. And then they have x86 assembly. Now, that x86 code is for running on Intel chips and AMD chips. They also have AVX2 code, which is for running on Intel chips and AMD chips. But not every Intel chip has AVX2 instructions. AVX2 is 256-bit vector instructions. Intel started putting AVX2 in their chips in 2013 with the Haswell processor, but not every Intel chip has AVX2. AVX512, these are 512-bit vector instructions. Intel started putting those into their chips, but most of the Intel chips don't have AVX512. And so depending on which machine you have, maybe you can use the AVX512 software, or maybe only you can use AVX2, or maybe you have to use this one, or maybe you're using an ARM CPU, and they have some ARM optimized software. You can always use the reference software. You can just say, I'll compile the reference software with my optimizing compiler, and that will give you code that works on whatever CPU. But it's not very fast. If your machine has AVX2 instructions, you get much better performance out of this AVX2 assembly language instead of using the reference code. Compilers are not very smart about making code run fast. Humans are better at making code run fast. And so they have many, many, many implementations for different chips. Plus, what is this times 8? Times 8 says I have 8 different inputs, and I want to hash all of those inputs. And now they have a function which says I take all 8 inputs, I hash this one, I hash this one, I hash this one, I hash this one. It's all separate, but that's faster than hashing each one, first this one, then this one, because they can use vector instructions in a better way. And so there are many of these times 8, times 4, times 2 functions. And again, this is faster than what the compiler can figure out. Another example, if you look at the NIST post-quantum cryptography competition, then they have, well, in the current round, there are some lattice systems, some code-based systems, some hash systems, one isogeny systems, some multivariate systems, and these systems all have hand-optimized code. They all have AVX2 code. Some of them have more. Some of them have ARM assembly, for example. But every single NIST submission, every single post-quantum proposal for standardization and for usage has fast code written to use 256-bit vector instructions. And whichever ones end up being deployed, they're going to do more of these implementations. So there's many, many different versions of the software for these cryptographic systems. Now, there's a very useful idea which people have been trying for many years, and what I want to convince you of in the rest of this talk is that actually, in many cases, this is something you can use now, and it works great. And what is called symbolic testing, this is the idea that you can check your optimized software and your reference software always give the same results. Now you're thinking, okay, testing, yeah, I do that. I try my reference software on some input, and I try my optimized software on some input. And then maybe they produce the same results, good, or maybe it's different results, bad. And then I try another input, and okay, that's normal testing. Symbolic testing says you try all possible inputs. Now that might sound like there's too many, it's too slow. You can't do that. But there are fancy techniques that people have developed for doing symbolic testing. And because of those techniques, symbolic testing is something that sometimes you can actually use now. So, main thing that I want to convince you of is that the tools that exist right now are something that you can use to verify some important cryptographic software. Not complete post-quantum systems yet, but some subroutines you can verify. And you symbolically test that the reference code is always equal to the optimized code and the reference code for every input give you the same results. Now, I'll be telling you from the user perspective what it's like using one little tool called Safe Rewrite, which you can find at pqsrc.cr.yp.to. This is something which is just a little Python script. If you look at it, it doesn't do very much. But that's because it's using all sorts of useful tools. Now, one of these, Valgrind, for any programmers in the audience, you should be using Valgrind and Address Sanitizer. These are very useful tools already. And that's sort of the very start of doing symbolic testing, is these tools which can understand what your code is doing symbolically. Then inside Valgrind, there's a library, which I won't say much about, but just to point to one of the most important pieces, Vex is a library inside Valgrind. There's another tool, the Z3 theorem prover. This is an example of what's called an SMT solver, satisfiability modulo theories. It's something which can say, for example, yes, this code is always equal to that code, and it can do fancy reasoning to figure that out and guarantee, yes, it's always correct. And then on top of these, putting all of these together, just right under Safe Rewrite, Safe Rewrite is using a toolkit called Anger, anger.io. There's a graphical user interface if you want to try Anger yourself. You might like the graphical user interface just because of the name. It's called Anger Management. But in this talk, I'm just going to be doing command line things. So Safe Rewrite uses Anger, which uses Z3, uses Vex inside Valgrind. Safe Rewrite also uses Valgrind separately. Okay, so what does Safe Rewrite do? Here's an example. This is cryptographic code. This code works correctly, but some people have gotten this wrong. So, what is this code supposed to do? Well, this is inside one of the post-quantum systems, a lattice-based system called Frodo. Frodo is a KEM, a key encapsulation mechanism. It's an encryption mechanism. And one of the things that it does, there are many subroutines inside Frodo, and one of the subroutines is simply comparing two arrays. The inputs here, x and y, these are arrays of 16-bit integers. Each one has 64 16-bit integers. And what this subroutine does is it says, well, if x0 is different from y0, return -1. If x1 is different from y1, return -1. If x2 is different from y2, return -1, etc., etc., etc. If all of the x's, the 64 x's, equal all of the y's, 64 y's, then the code returns 0. Now, this subroutine is something that I wrote from the specification. Frodo says, this is the comparison that you're supposed to do. Very easy function, took just a moment to write. Now, when you ask safe rewrite, what do you think about this code? This is the reference code. So before looking at optimized code, let's look at this reference code. So you just run safe rewrite with that code, and it says, well, first of all, Valgrind failure. Now, what is this Valgrind, unsafe Valgrind failure? What does that mean? Well, safe rewrite says, I tried running that code and using Valgrind to figure out what it does. And Valgrind told me that there were branches based on x0 and y0. If those are different, then it does a branch, does an if. And that's something that leaks secret information. If you think about it, if x0 equals y0, then, well, that will be going through the next part of the loop. And then if x1 equals y1, goes through the next part of the loop. If they're different, the function stops. I mean, let's go back to the code here. If any xi is different from yi, then the function will stop at position I. Which means the time taken by this code is different depending on how much of x equals how much of y. And usually one of these is secret data, and then somebody can use the timing of this to figure out, they'll try different x's if y is the secret, and then they'll figure out which x0 matches y0. And then once they know that, they'll figure out which x1 matches y1. And then, so they can figure out all the secrets by trying different inputs. Okay, so safe rewrite says this reference code is not safe because it's not constant time. And it also quantifies this. So safe rewrite will tell you that unrolling this code splits it into 65 cases. Maybe x0 is different from y0, that's one case. Maybe x0 equals y0 and x1 is different from y1, that's another case. And there's 65 possibilities in this code. Safe rewrite always unrolls whatever code you're looking. It only handles fixed length inputs, and whatever those inputs are, it will unroll all of the loops that happen in processing those inputs. All right, so this is safe rewrite trying one compiler, Clang. Now it also tries another compiler with different options, and again it says Valgrind failure and says unroll split 65, and then it says equals ref with Clang. So this is saying safe rewrite compiled the reference code with Clang, compiles it with GCC, and then looks at the binaries and says, those binaries always produce the same outputs, which is what you expect. I mean, Clang and GCC should produce the same results as what the original code says. That's an example of symbolic testing. This is something where if you normally look at Clang and GCC and you look at their binaries and there's some bug in GCC or a bug in Clang, then, well, maybe it passes all your tests. But no, symbolic testing says they always match. Maybe Clang and GCC have the same bug, but this is good for checking if there are compiler bugs. Now let's try another version of the same function. This is reusing the C library. Don't write your own software to do this comparison. There's a standard C function called memcomp. So, okay, include string.h and now compare why is it 128? Well, there's 64 16-bit integers, so that's 128 bytes inside X and 128 bytes inside Y. Now, if you try safe rewrite on this code, then first of all it says Valgrind failure. memcomp takes variable time. Actually, it shouldn't take variable time. If the people who wrote memcomp were optimizing it better, then it would take constant time in all cases. Sometimes it does, but anyway. Memcomp for the compiled code with GCC and Clang takes variable time. And also, symbolic testing says, hey, this is different from the reference code. The reason it's different is the original code was returning -1 if the X and Y were different. This code, well, if you look at the definition of memcomp, it says it returns something non-zero if X and Y are different. Okay, so let's fix that. So this code is calling memcomp, and then if the result is not 0, it returns -1, and otherwise returns 0. All right, and now safe rewrite says this equals the reference code. Good. But, well, it still has branches based on secret data. And this is basically the original Frodo code for this subroutine. The official Frodo software submitted to NIST for the post-quantum competition used memcomp, and then, well, last year there was a timing attack which showed that here's how you can extract secrets out of Frodo. So a complete disaster for the software because it has branches based on secret data and takes variable amounts of time. All right, so Frodo, they said, oh, there's an attack, we can fix it. Here is the official Frodo June 2020 memory comparison code. Well, it's a little bit weird. There's these logic operations, there's an OR, well, there's an XOR and an OR, and there's shifts, and then different integer types running around. Well, okay, they published this code and said this, I mean, this is really, all the previous ones were just simple examples, but this is the real Frodo code. Now, let's try testing this, and let's make sure that this always works. I mean, looking at it, it's a little complicated. I mean, somebody could make a mistake here, right? Would it be obvious? I mean, does it look correct? I don't know. So let's try testing this. Now, the interface is a little different. Well, different function name, but also there's a variable length. So let's make a little wrapper, same function name now, and the length is 64. And that's 64 is the number of positions in the two arrays. Okay, so I took the Frodo code, and I wrote these 3 lines, and then the reference code that we saw before, and asked safe rewrite, does this match the reference code? I should say, if you want to test variable length code, you have to plug in particular lengths that you care about. There's a limitation of safe rewrite. Again, it always unrolls everything. It only handles constant sizes of inputs. But okay, that's what Frodo uses, is some constant sizes, 64 and some bigger sizes. All right, so safe rewrite says, this is constant time code. Good. No more timing attack. Now, safe rewrite also says, it's different from the reference code. Maybe it's because of the -1 versus other non-zero numbers. But no. This code, there's a more serious bug. And because of this bug, it's actually very easy to break the Frodo official software from last year. Now, this is something where in December last year, this was announced that, oops, there's a bug in the new Frodo software, and you can exploit this. So they fixed the timing attack and then made an exploitable constant time version. And now here is working code for doing the same thing. This is another version of the same comparison, which is constant time. And I mean, looking at it, again, there's there's the logic operations here, and there's shifts, and something's happening, but like it looks sort of like the previous code, but you have to think, like, does this work correctly? Or, instead of thinking, you just use safe rewrite, and safe rewrite says this equals the reference code, and this is constant time. So this is finally a safe rewrite of the reference code. All right. If you download the safe rewrite package, then you'll find 10 implementations of this function, where one of them is written in assembly. Now, this one is taking the OpenSSL crypto memcomp function, which is, so OpenSSL for many years has its own version of memcomp called crypto memcomp. There's memcomp from the C library, and there's crypto memcomp from OpenSSL. The reason for crypto memcomp is to run in constant time. But they also have bugs for some versions of crypto memcomp. For example, 2018, for HP chips, which are not very popular, but there used to be some CPUs called HP PA-RISC CPUs. And these CPUs, they wrote crypto memcomp in assembly in constant time for these CPUs. And, well, that code had a serious bug. So it only checked 1 bit out of every byte. Oops. If they tested enough, they would have found this. Or safe rewrite can automatically find these bugs. There's also more functions. If you download safe rewrite, there are many, many examples. Now, some of the examples are just to give you examples of what safe rewrite does for different kinds of bugs. What happens if there's a buffer overflow? What happens if you're not reading enough data? All sorts of different API issues and memory issues. And these simple functions will show you what does safe rewrite do, what will these tools tell you when you have different kinds of bugs. Some of these functions are more serious cryptographic subroutines. And this is something where this is, well, getting rid of possible bugs in real cryptographic software. I'll give you one bigger example of that on subsequent slides. Whenever safe rewrite says that the optimized code is different from the reference code, then it says, here's an example of inputs which give you different outputs. And then you can try those examples and say, okay, this is what the code is doing differently. You can use a normal debugger. There's different ways to check those examples and see what's happening. Sometimes, if you do normal tests, just try some random inputs or try fuzzing for structured inputs, sometimes you can find the same bugs without symbolic testing. But sometimes, it's really hard to find the bugs. Some of the bugs that have been found in cryptographic libraries were not found by normal testing. They can be found by symbolic testing. I should warn you, if you download and try this package, it will use every core it can find. It will see how many cores you have on your CPU. It'll look at your SSH config and log into every, no. It won't SSH, but it will use many cores, and it'll use lots of memory. So what you can do to just try some simple examples, like the comparisons, is set sticky bits to decide which of the source examples you want to try. For example, just the comparisons, and then it finishes quickly, even on a laptop. Okay, I said I would give you a big example. So this is a subroutine which is one piece of one post-quantum function. This post-quantum system is called ntrue prime. It's another lattice-based system. And this one, well, if you look at the AVX encode.c, this is again using 256-bit vector instructions. And this, for one key size, for 761, this key size is using 245 lines in this subroutine. And then each different size has another 200 lines for this subroutine. Now, all of these C files are generated automatically by a 200-line Python script. So instead of 200 lines of C for every different size, you could read 200 lines of Python for all the sizes. But do those 200 lines of Python work correctly? It's not easy code. The C code is not easy. The Python code is not easy. It's not obvious what the code is doing. The reference code for this encode function, this is a much, much smaller piece of code. There's a 38-line encode.c, which does whatever this encoding is doing. And that is something shared across all the sizes. And then there's a little wrapper, that's easy code. That's 18 lines, which you can look at and check by hand. Now, is the optimized code the same as the reference code? Well, you ask safe rewrite, and it takes a little time, and then says, yes, the optimized code is doing the same as the reference code. So if the reference code is correct, then this AVX code is correct. This is part of the encode.c. This is an example of why you don't want to do this by hand. I mean, even writing a Python script which generates this is not straightforward code. There's all sorts of vector stuff happening and permutations between different vector positions. Basically, every line has another vector instruction. Calling this C code, well, it's C plus vector intrinsics to use these 256-bit vector instructions. And verifying 200 lines of code like this times different sizes, or verifying the Python code that prints out this code, it's not fun. But using safe rewrite, it's just automatic. All right, I have one last slide here just to give you an idea of what things are happening with safe rewrite. I've given you examples where it just works. And it says, yes, the reference code for this subroutine matches the optimized code. But if you try bigger examples, then it will suddenly get very, very slow and use too much memory and use too much time. Safe rewrite, it has a limit on how big the examples can be. But there's work for extending it to handle more types of post-quantum crypto, more types of pre-quantum crypto. Also, for checking that the code works correctly, it's good to have not just C reference code, but Python reference code, because Python code is simpler. And that's something which is planned to have safe rewrite taking Python as input, so then you can have the simple Python reference checked against the C code. And then there's more things to try to speed it up and make it easier to use for software engineering and to make sure everything works correctly. And finally, last lines here, there are various other projects that you should take a look at. I'll mention one of these, which is CryptoLine, which is developed right here at Academia Sinica, and you have the top experts in the audience. Well, all of these projects have different cool things they can do, and unfortunately, I don't have enough time to go through all of them, so I will stop here. Thank you for your attention.
Okay, so I can translate any questions if needed. 就是我这边都可以中翻英，如果有任何人有问题的话。
Is this okay?
Yeah.
You have warned us that this software safe rewrite spend a lot of time and use a lot of memory when you use it. For example, in just simple encode.c or even simpler comparison. So what is that? What exactly is the amount of time and memory we use? Can you give an exact example? For example, in the comparison case, how many memories are used, and how much time it used in some specified CPU?
So the comparison example actually is reasonably fast. It's not something that you would want to do inside a development cycle. I mean, we're talking like on the scale of a minute, which you don't want to sit there waiting a minute for the computer. But as part of like a continuous integration process, then a minute is fine. Some of the bigger examples, like the encode, doing that one fully is significantly longer, but I mean, less than a day. And then some bigger examples, the time can really explode because these, I mean, symbolic testing, and in particular the things done inside Z3 in the theorem prover for SMT solving, they understand many things, but if it's just a little too complicated, then they sit there forever. I mean, eventually, in theory, they'll finish, but they might use a ridiculous amount of time. I mean, in the end, it's possible for these SMT solvers to fall back to basically trying every input, which, I mean, something like the comparison example, it's obviously much faster than trying every input. But in the end, the SMT solvers, well, you can easily make cases where it just gets very, very slow, very, like suddenly super slow. So then there's various games, well, the cuts line here, there's various techniques that are used to use SMT solvers for parts of your reasoning and then put together several different chains, like make a chain of reasoning from saying, here's your optimized code, and match that up to your reference code. And then the memory is, again, it can explode to some unreasonable amount. That tends to be less of a problem than the time, but it can be that the memory just, if you don't have a reasonable amount of memory, you can get into trouble with memory.
We have 3 more minutes. Any more questions? 还有问题吗？ So a question which is what other languages are you hoping to support?
So currently, it will take whatever C code you give it, or assembly, or Rust. There's a few Rust examples. And then compile those to machine language. And then anything that can be compiled to machine language should be easy to integrate, because Valgrind understands machine language, and Anger understands machine language. So it's anything that can turn into a binary, you can, in principle, use right now. And the examples, again, are C, assembly, and Rust. Now, in reality, something like Python, if you compile Python into, well, machine language with tools like Cython, for example, or just running PyPy inside an emulator, you end up with code which is much too slow, like much too big for these tools to read through. And that's another of these sort of failure cases where in theory it could work, but in reality it's too slow. So the idea of supporting Python is to have Python converted directly into unrolled code without going through binaries. And that will be something which avoids all the complications of dealing with what happens when you compile Python. But anyway, in principle, it can be any language that's converted into machine language, plus the idea is to support more languages that are unrolled through extra support for those languages.
Any more questions from the audience? 还有问题吗？那如果没有的话，就谢谢讲者。